So that is STP. So if it says, hey, these are the conditions, it's at STP, you automatically know, I know the temperature, it's 273, I know the pressure, it's 1 atm. If I need to convert it, I'll convert it. Okay? So, with that information, we're going to look at problem number 2, practice. Problem number 2, in the middle of page 375. And we're going to do that calculation. We've already done one of these. We did one of these on Wednesday. So you're going to take the equation, combined gas law. You're going to have 5 of those variables, and you're solving for pressure. What I want you to do is ask for the pressure in pascals. Let's leave it in atmospheres. So, problem number 2 says, on page 375 in your book, says a 700 milliliter gas sample at STP is compressed and reduced to a volume of 200 milliliters. And the new temperature is increased to 30 degrees Celsius. You need to find the pressure. And I want you to find it in atmosphere. So go ahead and do that, and I'll come around and check your work. If you would do that. So we got molar volume at STP. Is always going to be 22.414 liters per mole. So the conditions have to be perfectly at perfect temperature, perfect pressure. And if we'd have 22.414 liters, that would be 1 mole. Okay, so let's say we double our volume. What happens to our number of moles? Double. We got twice. We got 2 moles. So we can use this setup to do any problem that deals with standard temperature and pressure of a gas. We say, hey, it's standard temperature and pressure. We can always use this problem to figure out moles. So we got moles that kind of come in to play that we're going to use. And this is the answer you're going to get in your lab, I hope. So we're going to set combined gas law to certain conditions, new conditions. Then we're going to figure out how many moles of gas, hydrogen gas, we form, how much volume it takes up, and all we have to do is take the volume divided by the moles, and if we do that, and we get close to 22.414, then we've done a good job of representing the law or looking at molar volume. Okay, any questions with that? Last thing you have to know is Dalton's law of partial pressures. I'm going to share that with you. Take about 5 more minutes. Talk to you about it. And kind of explain how you're going to use it in the lab. And then we'll have you guys partner up and do the lab. We're going to have you use the back lab because I've got those all organized. And while you're doing the lab, I'll help you. But I'll also be organizing some of these areas here so I can get reorganized a little bit. Okay? So if you guys use those back, you know, I think with our class size we can do that comfortably. We can do that. So, all right. So, want you to turn in your book to a place where it talks about this Dalton's law of partial pressures. And I need to explain that. And that's on page 365. Dalton's law of partial pressures. So John Dalton was the guy we had already talked a little bit about. He's the guy that came up with atomic theory. He says all matter is made up of indivisible particles called atoms. These atoms go together in whole number ratios when they form compounds. all atoms of the same element are alike. Atoms of different elements are different in mass. They're different in their properties. He's the one that came up with that. But he also looked at some ideas dealing with gases. Okay? So I'm going to use this analogy that sometimes being a wrestling coach will weigh in the morning and then go to the meet, and they have to be on weight or underweight or they don't wrestle. Okay? So they'll get there in the morning, they weigh themselves, and they might be a half a pound under. And so they've already maybe skipped a meal or two, so they're kind of hungry. So what they'll do is they'll take some food that they brought along, and they'll weigh themselves on the scale with that food to see how much they can eat. Okay? So it's kind of smart. I mean, they can eat that food if they're under. Okay? The scales are the same, and usually they're about the same. They're not much different. Okay? So how does that apply to Dalton's law of partial pressures? Here's what we do. What gases do we have in this room right now? Can you guys tell me what gases we have in the air? Okay? Oxygen, nitrogen. What else? Anything else? Just that? There's a little bit of argon, believe it or not, about 1%, a little less than 1%. There's way less than 1% of CO2. It's kind of like 0.04%. So it's a really, you think CO2, and you hear a lot of things about greenhouse gases, and it's just, they're building up. Well, the CO2 is much less than all of these three. Okay? You got a little bit of water vapor in the air. Okay? If we add those all up, let's say the pressure today is 1 atmosphere. A pressure on the barometer. It's not. We're probably a little bit less. What gets that 1 atmosphere? Well, it'd be the pressure of O2. It'd be the pressure of N2 added to the pressure of argon, added to the pressure of CO2, which is very minimal, added to the pressure of water vapor. These are called partial pressures. And if you add up all the partial pressures, you get the total pressure. So every gas contributes. So it would be like if we wanted the total weight of our class. Like if we get on an elevator and you start adding up the people and you're going, this is a 2,000 maximum elevator and I think we have more than that. I'm going to get off. Okay? Way more than that. I don't want to take a chance. Pressure of gases are the same way. You can add them all up and you get the total pressure. So whatever the room pressure is the partial pressures all added up. Okay? Now, I say that if we did a problem, real simple problem, and we had two gases, and we knew the partial pressure of one of the gases is 0.3 atmospheres. We know the total pressure is 1 atmosphere. What's the pressure, let's say N2 is the other gas? What would it be? You guys can tell me. What would it be? 0.7. Okay? Subtract 0.3 from both sides. 0.7. So this is what happens. You'll collect that hydrogen gas in there, but there's another gas in there. If you've ever taken a shower, hot shower for a long time, and you open up the door and you see this vapor in there, or if you've ever been to a swimming meet or at the YMCA and you walk in, does it feel a little bit stuffier, a little bit? You can feel the water vapor, can't you? Okay? So guess what's in that tube? If you were in that tube, would you feel water vapor? We'd shrink you down. You bet. So there's two gases in there. There's water vapor, and then there's also hydrogen gas. So when we do our lab, we want to concentrate just on hydrogen gas, and there'll be a problem that you'll have to do where you're going to have to subtract out the water vapor and just focus upon hydrogen gas. But when you get to that, if you need help, you can do that. But this is the setup. P total equals the P1, and those are just all the different gases you'd have in there and their pressures. Okay?